What's up, everybody? It's Dan from SageMathTutoring.com, and we're back with another video, this time a geometry video pertaining to things like cones, prisms, cylinders, things like that, studying surface area, lateral area, and all that good stuff. So I think before we dive into the problems here, let's get clear on the formulas first. Let's just kind of talk about the formulas that are involved, and we could also kind of go over this example here. So with regards to the formulas, um, let's see. So for prisms and cylinders, the surface area is going to be the area around the whole thing. So it's literally the area around the whole sort of three-dimensional figure. I like to think of it as like if you were to spray paint the entire outside of the figure, how many square units of spray paint would be required to actually cover this, okay? Now, uh, mathematicians saw some reason to separate the surface area sort of concept into the lateral area and also just the general surface area. Now, the lateral area is essentially like if you have a prism, let's say it's this sort of rectangular or cube type prism or a square prism. You have the base on the top and then you got the base on the bottom, right? Well, the lateral area would be all this shenanigans, the blue stuff that's on the outside. That's the lateral area. So it's the surface area of the entire figure without counting the area of the two bases, okay? So that's what lateral area is. And the way that my student's teacher seems to have described it is that the lateral is the faces without the base. So L equals perimeter times H. Now that's actually very interesting. It's going to be the perimeter of the base, perimeter of the base. So in other words, lateral area is going to be whatever this perimeter is, this green perimeter is, times the height of the entire figure. All right. So that is what's happening when it comes to the lateral area, at least of a prism, and the lateral area, we could say, even of a cylinder, because let's look at this. This is, believe it or not, the lateral area formula for a cylinder, believe it or not, is really the same thing. It's really going to be the perimeter of the base, but it so happens that the base of a cylinder, right, is a circle. So it's going to be the perimeter, we could say the perimeter of the base times the height, okay? So it's really the same concept. It's just that we have a special word for the perimeter of a circle. We call it the circumference, and the circumference is always going to be 2 pi r, which is why it's right here, okay? So just keep in mind, though, that this formula is essentially the same thing as this formula. It's just that we use a p to represent the perimeter of a polygon base, and we use 2 pi r, also known as the circumference, to represent the area, or the perimeter rather, of the cylinder base, okay? So that is what's happening when it comes to lateral area. My student's teacher also decided to sort of remind, what the perimeter would be of a base like this. It would be 2 times length plus 2 times width, and that's the case if you're dealing with a quadrilateral, I guess. Yeah, quadrilateral like that. Rectangle, if you're dealing with a parallelogram base. So let's see, surface area, right prism without the base. Okay, so surface area includes the area of the bases. So notice how the surface area formula is literally the exact same thing as the lateral area. Look, there's an L here, there's an L here. So it's literally going to be the exact same thing, except now you have to add the area of the two bases. So they use a capital B to represent the area of the bases. So they say it's going to be the lateral area plus 2 times B. Makes perfect sense. You already find the surface area of the lateral area, right? And then you find the area of this base, and you find the area of this base, and then you add that on top of it, okay? So that is the case with that. Let's see, surface area of a cube. Okay, that's sort of a special case. Let's look at the surface area of a cylinder. Well, guess what? It's going to be the lateral area all the way around, plus the area of the two bases, right? So we have the area of this base and the area of this base. Now, I would mention, I would really kind of emphasize this fact right here, which is that because the area of a circle, because the area of that circular base is pi r squared, we could say that the surface area of the cylinder is L plus 2 pi r squared. That is nothing more than rewriting that b as pi r squared, okay, because they are the same, right? It's right here. So that is what's happening when it comes to the lateral and surface area of a prism and a cylinder. Now, let's talk about this. The surface area of a cube is really going to be the same thing ultimately. You could sort of default to this um, formula here. However, the surface area of a cube is such that it's kind of a special case because the area of each of these faces in a cube is going to be the same. And we get those faces by multiplying side times side, right? Side times side. We don't need to say length or width or height or whatever, because all these side lengths are the same, so there's no need to use different variables. So we have side times side, that's going to be the area of one of these faces, right? And therefore, you take into account the fact that there's 6 of these, so it's going to be 6 times the area of one of these, also known as 6 times side squared. All right, so that's that. Let's take a look here at actually, let's not bother with the examples. Let's actually get right into the problems. So looking at problem number 19, find the lateral area and surface area of each right prism or cylinder, round to the nearest tenth if necessary. Okay, so with regards to problem number 19, we know that L is going to be perimeter times the height, or we could say, in the case of a cylinder, right, it's going to be 2 pi r times the height. So that's going to be easy enough. The lateral area is going to be 2 times pi times whatever the radius is. Now, what is the radius here? They give us the diameter of this circle. It's 10, so we should know by now that the radius is half of that. So we're looking at 2 pi times 5 times the height. Now, I know this is lying down on its side, so it might be non-intuitive to think of this 20 yards as the height, but the reality is this is the height. Think of the height as the distance between the two bases, okay? So we have 2 pi times 5 times 20. In that case, we would have, therefore, 200 pi, and I believe most teachers will be fine with you leaving it like that. Now, they want the surface area as well. The formula for surface area is right here. We could think of this too, but it's right here. I'm going to use that second one because it's a little bit more precise. So we have L plus 2 pi r squared. Well, we already know what the L is, don't we? We just found the L, right? Didn't we just find the L? It's 200 pi. All right, 200 pi plus 2 pi times the radius squared this time. Now we know the radius is 5, so it's going to be that. So it's going to be 200 pi. 5 squared is 25. 25 times 2 is 50. So we have 50 pi. And then when you sort of add that, it's going to be 250 pi. That's the surface area of the whole thing. Okay, now they say they want the lateral area of a cube with side length number 5, or 5 feet rather. Well, the lateral area, we sort of didn't discuss that. We discussed the surface area of a cube, and we discussed this formula right here, but I would like to use the exact same principle. The lateral area would just be the area all the way around, not counting the top and the bottom, right? Well, how many faces is that? That's 4 faces. So we're looking at 4 times side squared. That's going to be our L, we could say. And the side length is 5, so we're looking at 4 times 5 squared. 5 squared is 25. 25 times 4 is 100. So that's the lateral area. Now, if we want the surface area, we could always just use this formula here again, really. We could just say that the surface area is going to be equal to 6 times side squared. Well, the side length is 5, so it's going to be 6 times 5 squared. 5 squared is 25. 25 times 6 is 150. So that's the surface area of that cube. All right, looking now at problem number 21, an equilateral triangular prism with a height of 7 meters and a base edge length 6 meters. Well, let's get right to reminding ourselves that the area of an equilateral triangle, well, the area of any triangle is really base times the height times 1/2. So the area of a triangle equals 1/2 base times height. Now, it's also the case that we need to remind ourselves of a 30, 60, 90 triangle. So this is actually kind of an annoying problem, okay? So imagine we had a right triangle that was 60 degrees there. Let's say it's 30 degrees here. Well, hopefully my student remembers that if this side length, which is the short side that's across from the 30-degree angle, if that's A, then this hypotenuse is going to be 2 times that. And we can also recognize that this sort of other side would be A radical 3. Okay, so this is an A right here. That's an A. Now, because that's true, we could take note of the fact that the short leg will always be half of the hypotenuse here, or we can think of the hypotenuse as 2 times the short leg. There's that sort of relationship that can help you remember the situation. Now, why am I getting into 30, 60, 90? Well, because I can already see where this problem is going. They're sort of being weird with us. Equilateral triangle prism with a height of 7 meters and a base edge lengths of 6 meters. So let's go ahead and draw the situation. Let's imagine that's an equilateral triangle. Here's um, the rest of the prism, and we know that the height is 7, and we know, definitely not drawn to scale, but that's okay. So this is a 6, that's a 6, that's a 6. So what we actually have is sort of a triangle. I'll just do a little diagram that says that one side is 6, the other side is 6, and the other side is 6. And in order to figure out the area of this, well, we're going to have to find the base. Well, we have the base is 6, but we need to find this height right here. Okay, we need to find this height that we connected to the top like that. Okay, so the question is, what is the height? Okay, what is this height here? Well, it's up to you to recognize that whenever you sort of take an equilateral triangle, and you are cutting it in half in this way, what you've formed are two 30, 60, 90 triangles. It's the case that there is a 60-degree angle here. There is a 30-degree angle here, okay? Now, there's a right angle there. Now, it is the case that, therefore, this part is going to be half of 6. That's clearly 3. Okay, this whole thing is 6. Now, the red 3 corresponds with an A, so therefore this is going to be A radical 3, so we therefore know that this height is 3 radical 3, okay, this red height here, okay? So now we have the height of the triangle, which enables us to actually figure out the area of the triangle, because in order to find the area of a triangle, we need 1/2 base times height. So we're now looking at the area here. It's going to be 1/2 the base, which we already know is 6, times the height, which we now know is 3 radical 3. That's going to end up being 9 radical 3, and that's the area of the base. So we could call that B. Okay, we could call that B. Now we're going to be using that when we find the surface area. Right? We're going to be using that when we find the surface area, because the surface area formula requires us to know what B is. Let's figure out the lateral area really quick. The lateral area is nothing more than the perimeter of the base, which is 6 plus 6 plus 6, which is 18, times the height of the whole thing. The height of the whole thing is 7. So therefore, the lateral area is going to be 18 times 7, aka 70 plus 56, aka 126. So that's the lateral area. Let's go ahead and find that surface area. We know it's going to be the lateral area plus 2 times the base. We already know the lateral area. It's 126 plus 2 times the base that we just found, which is 9 radical 3. All right. And we have 126 plus 18 radical 3. Okay, so that's how you do that one. Okay, so now we're looking at problem number 22, a regular pentagonal prism with a height of 8 centimeters and a base edge length of 4 centimeters. So let's draw that. Here's a pentagon, okay, and then we have this prism situation right there. And we know that the height is 8, right? And we also know that the base edge length is 4, so that's 4 all the way around. Now, let's remind ourselves of the area of a pentagon, what that would be. That is going to be area of a pentagon, or area of really any polygon, is going to be 1/2 the perimeter of that polygon times what's called the apothem, which is denoted by that A there. Now, the apothem itself would be the distance between the center and one of the sides right here in such a way that would form 90 degrees. All right, so I'll call that A. Now, there is another concept that we're going to need for this one, and that is the fact that anytime you have a right triangle, and let's say you have this angle right here, and let's say you have also this side length right there. Well, it turns out that there is a way to find this value right there, which is x, okay? The way that you could find x is you could use tangent. You could say the tan of whatever that angle is going to equal 2 over x. Now, it turns out that that's going to be very helpful for our particular situation because when we analyze the pentagon, right, here we have this pentagon. When we analyze it, and specifically look at the apothem there, well, that apothem is sort of an unknown. Let's call it x. Like, we don't know what that is yet, right? But what we could do is we could recognize that there is indeed sort of a right triangle inside there. And we also know that this green part happens to be 2 because that's going to be half of this side length here. So really, all we need to do is get clear on what is that angle right there. What is that angle? Well, if you sort of analyze a pentagon just in general, and if you were to break that up into these like triangles, not right triangles, but just triangles, you would see that whatever this angle is, plus whatever that 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 angle is, x plus x plus x plus x plus x. Well, that's going to all add up to 360 degrees because that's the angle addition postulate. When you add all of these all the way around a full revolution, that's going to be 360 degrees. So therefore, we're looking at 5x equals 360. So dividing both sides by x gives us 72. So it's the case that one of these angles, right? One of these angles, or each of them, I could say, right, is 72 degrees. Well, if we were to draw an apothem straight down there, well, that angle would be half of the 72, so that's going to be 36 degrees. So that's a way of going about finding the angle that's inside this right triangle. Find out what each of these interior angles would be, and then divide it in half, and then you're going to get the angle that belongs inside the right triangle that you're analyzing. Okay, so that's how you sort of work with that. Looking, therefore, at this particular diagram, we can then say that that right there is 36 degrees. Now, therefore, we have a tangent situation where we could say the tan of 36 equals 2 over x. So I'm going to say that right now. I'm going to say the tan of 36 degrees equals 2 over x. Now, whenever I see an x in the denominator, what I like to do is swap it with the thing that's across like that. So it would be x equals 2 over tan 36 degrees. And if you plug that in your calculator, you're going to get approximately 2.8. 2.8. All right. So we're going to say that the apothem, therefore, is 2.8, which we need because we need to find the area of this pentagon. And we know that the formula we need is this one. So we can begin to fill out what we know. It's going to be 1/2 the perimeter. Well, what is the perimeter? The perimeter is going to be 4 plus 4 plus 4 plus 4 plus 4, aka 20, times the apothem itself. The apothem itself is 2.8. So that's going to be 10 times 2.8, aka 28. All right. So that's going to be the area of the base of that prism. So I do believe that that's going to be helpful for sure. So we have B equals 28. Now, with regards to the lateral area, however, when it comes to lateral area, all we really need is the perimeter times the height of the thing. The perimeter is going to be 20 um, times this 8, and that's, of course, going to be 160. So we can say L equals 160. And we also know that the surface area in general is going to be L plus 2 times B. So we can say S equals L, which is really 160, plus 2 times 28. All right. So in that case, we have 160 plus 56, which turns out to be 216. So that's the surface area. Lateral area is 160. Surface area is 216. All right, so let's look at the note cards here. When it comes to pyramids, first of all, pyramids are such that there's a polygon at the bottom, and then it kind of goes up like a teepee, like a tent, right, from there. And that's how you know you're dealing with a pyramid. You know you're dealing with a cone when the base happens to be circular, okay? Now, with regards to lateral area, we're going to have to introduce another concept called the slant height. Now, the slant height is not going to be, I'm not crazy about this diagram. So let me just draw that right there. I'm going to ditch the diagram altogether. So let's imagine we have a pyramid. Yay, it's got a square base. We have a point on the top, and then it's like that, and then it's like that, and then it's like that, and then it's like that. And then the slant height would be this sort of red line that cuts straight down the center in such a way that would form 90 degrees with the bottom part. Okay, so it's this red thing. So that's the slant height. Now, when it comes to the slant height of a regular pyramid, it would be that. And it turns out that the lateral area is nothing more than 1/2 times the perimeter of the base times the slant height. All right, 1/2 times the perimeter of the base times the slant height. Okay, simple as that. Surface area is just going to be that. Surface area is just going to be the lateral area plus 1 times the area of the base. Okay, before on the previous note card, it was 2 times the area of the base, but we only have one base now, right? We just have this one single base. So therefore, um, we only need to take into account one base. Okay, so therefore we could say that the surface area is really lateral area plus the base. Okay, that's just a simple way of putting it. This is a little bit more detailed because it turns out the lateral area is 1/2 times the perimeter times the slant height. So cool. Now, in the same way that rectangular prisms had much in common with cylinders, it turns out that pyramids have something in common with cones, and that it's really just the same deal. The lateral area over here was 1/2 times the perimeter times the slant height, right? Well, that's going to be the case here. It's going to be 1/2 the perimeter, I'll just do that, times the slant height. But the perimeter of a sort of circle, right, is pi, or 2 pi r rather, 2 pi r. So that's why we could say that these twos cancel. Next thing you know, you have just pi r l, which is exactly what we have here. Okay, pi r l. So that's the reality of the lateral area of a cone. Now, the surface area of a cone is going to be nothing more than the lateral area plus 1 times the base. So I will sort of rewrite this as L plus B. In a way, it's going to be the same deal as before, but we can have a nice detailed formula that says that L is really pi r times the slant height, and then the base is the sort of area of the circle on the bottom. So the base would be pi r squared. Okay, so that's that. All right. Looking at problem number 23, a square pyramid with side length of 15 and slant height of 21. We want to find the lateral area and the surface area of each right pyramid or cone. All right, so diving into problem number 23, let's see. A square pyramid with side length 15 feet and slant height of 21. Okay, so it would be something along these lines, right? And with regards to the slant height, I'll draw that in blue. That's this guy right here. And it so happens that the slant height is 21. All right, great. So pretty straightforward because focusing on the lateral area, it's literally going to be the formula here, 1/2 perimeter times the slant height. So I'll just say L equals 1/2. And the perimeter is going to be this 15 plus another 15 plus another 15 plus another 15. So that's 15 times 4, also known as 60. So it's going to be 60 times the slant height, which they gave us, that is 21. So that's going to be 30 times 21, which is 630. So that's the lateral area. Now, in order to get the whole surface area, we're going to take that lateral area that we just found and we're going to add the area of the base. So the surface area would literally just be 630 plus whatever the area of the base is. Now, the base is 15 times 15, and that is 225, right? 225. All right, and when we add those, we're looking at 855, it looks like, right? All right, so that is how you do that one. All right, so looking at problem number 24, a cone with radius 7 and height 24. So here's that cone right here. We know the radius is 7, and we know the height, in other words, the height from the sort of ground up there is 24, okay? Now, unfortunately, in order to get the lateral area, which is the first thing we do need the slant height. Now we have the radius, pi is just pi, but we need the slant height. So the first mission is to figure out this blue sort of slant height. And the reality is there's this triangle that's being formed. I'm sure some of you can see it. It's this yellow triangle that's on the inside. And of course, what we could do is we can go off to the side and analyze it. Okay, that's 24, that's 7, and we're looking for this blue line there. So that is going to be a matter of using the Pythagorean theorem, so we could call that C. And we're looking at 7 squared plus 24 squared equals C squared. And that's going to turn out to be, after all of your calculations, 25. All right. Now, it turns out that was a Pythagorean triple, so some of you may have known that right away. But nonetheless, the slant height is going to be 25, therefore. And now we're ready to figure out the lateral area based on this formula here. So that's just going to be pi. I'll just say L equals pi times whatever the radius is. In this case, it's 7 times that 25 right there. And 7 times 25 is 175, so that's just going to be 175 pi. Now, finding the surface area is going to be relatively easy in that we take that number that we just got, right, because we found L, we found pi r times the slant height. It's 175 pi, so we're just going to add the area of the base on top of that. So the surface area of this cone is therefore going to be 175 pi plus the area of the base. Now, the base right here, the circle, we haven't found the area for it yet, but we can remember, well, that's just pi r squared, right? That's the area of any circle. So it's going to be 175 pi plus pi times, and in this case, it's 7 squared. So therefore, we're looking at 175 pi plus 49 pi. And then when we add all that, it becomes 224 pi. Okay, so hopefully that's helpful for you. That is the surface area of that cone. And moving on to the next one. All right, taking a look at problem number 25 right here. A cone with diameter 20 and a slant height of 15. Well, they're giving us the slant height this time, which already is showing me it's going to be relatively easy compared to that last one. The diameter is 20, so that's their way of being tricky with this problem, because when it comes to the lateral area of a cone, of course, we need the slant height, and they gave us the slant height, right? The slant height is, looks like it's 15, right? Slant height is 15, but we don't have the radius yet, but as many of you watching probably understand, the radius is very easy to find. It's just going to be half of that 20. So we're looking at pi times 10 times 15, and then of course that's 150 pi. Okay, so that is the lateral area. Now the surface area is going to be a matter of, just like in the last problem, adding the lateral area to the area of the base. Now the area of the base is pi r squared, and we know that r in this case is 10. So we're looking at 150 pi plus 100 pi, and therefore we're looking at 250 pi. Okay, I kind of skipped a step right here. That's 100 pi. So that's how you do that one. All right, so looking at problem number 26 right here. Find the surface area of each composite figure. Okay, well, we have the pyramid on the top, which is right here. We have the pyramid on the bottom. Now, this looks like it's hard, but, well, I guess it is kind of tricky, actually, now that I think about it. They want the surface area. Let's be very clear. We don't want to count the bases, right? Because the bases are sort of inside the figure. So that's the first mental note you should be making, is that, oh, okay, cool. So when I the surface area all the way around this whole thing, I don't want to mention anything about these bases. So in reality, the answer to this problem is going to be the lateral area of the top figure, right? It's the area all the way around the pyramid, not the base, plus the lateral area of the bottom figure. It's going to be the area, surface area, we could say all the way around, but not including the base itself. So I'm sort of a fan of using big picture views. So we have the lateral area of the top plus the lateral area of the bottom, and that's going to be our answer. Okay, so what we could do is we could break it down and ask ourselves, well, what's the lateral area of the top? Now let's remind ourselves, when it comes to a pyramid like this, the lateral area is 1/2 the perimeter times the slant height. Okay, so the lateral area of the top is going to be 1/2 the perimeter, which I'm not so sure what that is yet, times the slant height. Now the slant height is 30, so we could begin the process of fleshing that out. And then the lateral area of the bottom is going to be similar in that it's going to be 1/2 times whatever the perimeter is, um, times the slant height of the bottom, and that's given. And it's the case that that's 20. So I don't really need to write equals question mark every time. The bottom line is we're going to just work this out. We're going to simplify it, and that's going to be our answer. Okay, so I'll actually get rid of this. All right, so the question then is, what is the perimeter of the top and what is the perimeter of the bottom one? And it's the case that the perimeters are actually the same. Okay, so that's something kind of interesting. Now, this side length is 8, and it appears as though this is certainly a square base. And in fact, I do believe that I feel like they should say that. Okay, they should give us more information on that one. Yeah, should we just assume that it's 8 all the way around? Hmm. In my opinion, unless I'm making a mistake, in my opinion, it's okay to assume that that's 8, that's 8, that's 8, because I feel like we've been dealing with square pyramids quite a bit. So I'm going to go with that. I'm either making a mistake or I'm correct in that assumption. And if I'm correct in that assumption, then really the problem should have given us more information. So regarding the perimeter, it's going to be 8 plus another 8 plus another 8 plus another 8. So that's 32. So we're looking at 1/2 32 times 30 here and 1/2 32 times 20 over here. So this is going to be 10 times 32, which is 320. And this is going to be 15 times 32, which is 480. So that's 480 right there. And in that case, we're looking at 800 square units, 800 feet square, we could say. All right. So that's how you do that one. Okay, so looking at problem number 27, this is going to be a matter of adding the lateral area of the top cone, the lateral area of the bottom cone, and the lateral area of the cylinder. Once again, we're not going to be counting the surface area associated with the bases because the bases are sort of inside the figure. Now, one thing I'm noticing is that this cone is the same size as that one. So when we sort of create the big picture formula, we could say that it's going to be 2 times the lateral area of the cone plus the lateral area of the cylinder. And that's going to be the answer. So once again, lateral area, at least when it comes to a cone, is pi RL, right? Pi RL. So let's just piece it together bit by bit. I don't want to do too many steps like in my head. So it's going to be 2 times pi RL here. And over here, it's going to be the lateral area of the cylinder. And as a reminder, the lateral area of any cylinder is going to be 2 pi r times h, right? So let's just write that down, 2 pi r h. And piecing it together further, we have 2 pi times the radius. Now the radius is given, that's 8. The slant height is given. The slant height happens to be 12 here, which is great. It's always better when they give it the slant height. So we have 12 there, plus 2 pi times the radius, which is 8, times the height of the entire cylinder. Not the height of the whole figure, but the height of the cylinder part, right? That's this part right here. So that's going to be 16. Okay. So let's see. Well, I'm going to be fancy. So we got a 2 pi, we got a 2 pi. We also have an 8, we have an 8, so that's a GCF. So we could take out 2 pi 8 and multiply that by 12 plus 16, right? So I'm just going to do it that way. So that's 16 pi times, looks like that's going to be 28. And 16 times 28 is 448. So it's 448 pi. Now, just keep in mind that um, you could have just multiplied that out. That would have been 16 times 12 pi. This would have been 16 times 16 pi. And then you could have added these. Okay, I kind of did a weird thing where I factored out the greatest common factor and just because I saw an opportunity to. So anyway, that is how you do problem number 27. So hopefully that was helpful to those of you watching. Thanks for watching, and comment below if you noticed any mistakes or even if you see a better way to go about things. I feel pretty good about that. Careless mistakes, though, do sneak up on me for sure, but I do feel good as per usual about the process itself. So anyway, I will talk to you later. Have a good one.